Now let's talk about some of the first concepts with perturbation pressure. Perturbation pressure, remember we talked about that diagram, that tree diagram of how perturbation pressure comes about. We talked about a linear component and also nonlinear component. Well, the nonlinear component can be broken down into a shear component, subcomponent, and a fluid extension subcomponent. We're going to focus especially on the shear component. And the shear component means that wherever we have perturbation spin, or effectively from a base state we induce vertical vorticity, or spin about a vertical axis. Wherever we have spin about a vertical axis, regardless of whether it's cyclonic or anticyclonic, because we're squaring the perturbation vertical vorticity term, that will always induce a perturbation pressure deficit. So any spin about a vertical axis will give us a perturbation pressure deficit, or a perturbation pressure low. Now, why is that the case? Why do we get a perturbation pressure deficit, or a mass deficit, wherever we have spin about a vertical axis, regardless of it being cyclonic or anticyclonic? Well, think about whether when you're on a merry-go-round. You're on a merry-go-round, whether you're spinning counterclockwise or clockwise, you're going to feel a local centrifugal acceleration, or a fictitious force that's pulling you away from the axis of rotation, directed outward from the axis of rotation. Now, so that you don't go flying off from the merry-go-round, there is an inward directed force that opposes a local centrifugal acceleration that is working to allow you to maintain circular balanced motion so that you can maintain presence on the merry-go-round safely. Now, it's the same thing in the atmosphere. If the atmosphere is all of a sudden going to induce spin about a vertical axis, and we'll talk about reasons why soon, then that spin associated with circular balanced motion is going to involve an outward directed local centrifugal acceleration that's going to have to be countered by some inward directed force, or an acceleration. Now, how does that atmosphere accomplish it? It accomplishes it by inducing a deficit of mass, causing the pressures to drop out, just like a vacuum cleaner, around that now forced axis of rotation, because we've induced a deviation, a perturbation from the base state, which will bring pull mass inward, potentially upward as well, and that vacuum cleaner, that perturbation pressure deficit aloft, is going to allow the outward directed local centrifugal acceleration to be balanced by an inward directed perturbation pressure gradient force to permit the maintenance of circular balanced motion. So let's consider a straight hodograph. Now, a straight hodograph, want to indicate, means unidirectional shear, not necessarily a unidirectional wind profile. So think about a straight hodograph that lies along the x-axis, going eastward, say, from the origin. In that case, the flow at every level above ground is out of the west, it's unidirectional wind, and it's unidirectional shear. But now say we have a hodograph that is not along the x-axis, but is parallel, congruent, and shifted northward from the x-axis. Well, it's still a straight hodograph in that case, so we're effectively talking about a line that looks like an equation of a line. Let's see, in this particular case, it would be y equals some number that's equal to the y-intercept of that line. West-east looking plot, for instance, that is above or north of the x-axis. Well, in that case, we're going to have, again, the shear is going to be parallel at every single point on the hodograph, all out of the west. But because that hodograph in the lower parts is all southerly and southwesterly with increasing height above ground, that hodograph is going to correspond to a veering wind profile, even though it's a straight hodograph. So again, a straight hodograph could mean unidirectional wind, but it doesn't necessarily. It means unidirectional shear. Because a straight hodograph, every single tangent is going to be parallel to one another on that hodograph. Now we're going to layer on not only a straight hodograph, but we're going to make it even stricter, also say unidirectional wind profile. So now we're going to make sure that we have both unidirectional wind profile and unidirectional shear profile. So we're going to be having a stricter case of a straight hodograph. So the shear and wind vectors are all parallel to each other. So let's try to imagine this here. We have a westerly flow that increases with height above ground. We're looking off to the east along the x-axis. The y-axis, or south to north, is now going into the side here, and then the z-axis is going up. So what I'm sketching here is at the origin, we have our westerly winds are increasing with height above ground. We know from the right-hand rule, and even confirming our now understanding of how we can derive the horizontal vorticity from the hodograph. If we sketch this hodograph, again, we have increasing westerly flow with height above ground. We get that first example that I gave of a hodograph that lies along the x-axis over here. We know the shear profile is always westerly, and using the concept of the horizontal vorticity lying to the left of the hodograph, that is consistent with the right-hand rule, curling our fingers down the faster flow down towards the ground and up around, bringing us with a south to north horizontal vorticity. And I'm going to use the term of horizontal vorticity and vortex tubes and vortex lines, excuse me, I shouldn't say horizontal vorticity, but rather vortex vectors, vortex tubes, vortex lines are all going to be synonymous. Now I want to reiterate that this is the hodograph over here. So we're not looking actually up along this axis over here. We're looking at this hodograph, which is going to correspond to that vertical shear of the horizontal westerly wind, increasing westerly wind with height above ground. That's going to result in these vortex tubes that go from south to north. That's why I have it angled over here. That vortex tubes, vortex line, horizontal vorticity that's going from south to north. Again, angled perpendicular to the hodograph going from south to north along the y-axis. Now, we're going to take this vortex line right over here, and remember we talked about there being sufficient conditions for an updraft to develop. All right, so we're going to take this south to north vortex line. We're going to induce an updraft. What's that going to do? It's going to take that vorticity and it's going to tilt it into the vertical. We're going to effectively take that vortex tube. The updraft comes along, kind of treats it like a material curve and draws it upward. Drawing that upward from that vertical motion is going to result in a component of the vortex tube that is directed upward for cyclonic vorticity to the right of the shear vector, or to the south of that updraft relative to that westerly shear. And then an anticyclonic or downward directed horizontal vorticity, because remember our horizontal vorticity is pointed northward. Now, because we're drawing that vortex tube upward, we're going to have a downward component of that vorticity on the north side of that updraft, or to the left of the westerly shear vector. So again, cyclonic vorticity to the south, anticyclonic vorticity to the north. However, in both cases, we're going to have that perturbation pressure deficit is going to be negative regardless of the sense of rotation. And remember, that is going to be associated with the process of tilting of that horizontal vorticity. Now, that initial updraft right over here, that initial updraft is not rotating. It's not rotating at all at this point. You might wonder, well, why is it not rotating? We're going to talk about this in just a moment. But this initial updraft is not rotating. Now, we do get upward vorticity, but this initial updraft, it's not rotating. And we're going to talk about why in just a moment. So again, at this particular stage in the process, we indicated that there are no rotating updrafts. We simply have negative or low perturbation pressure on both cross shear flanks of the initial updraft, that is, one to the south or on the southern flank of that initial updraft, and that is to the right of the westerly shear vector, and then also one to the left or to the north, or flanking on the left side of that initial updraft relative to the westerly shear vector. Now, why is this the case? Well, we know that initial updraft, again, we're not allowing for any convective interactions along boundaries, etc. That initial updraft is just going to be moving along the mean wind, what we'll call it the C vector. That is not experiencing any propagation yet. There's no propagation at this point yet. The only reason for convective motion is going to be driven by advection. And we already talked about, in our particular case, with the unidirectional wind profile, that's all going to be carrying that updraft from west to east. So all of the vorticity for that updraft's inflow is crosswise, perpendicular to the inflow. Let's look at this. So we're looking back at a hodograph now, and we have our updraft, which is just being carried along the mean wind, which is all westerly within the convective layer, and that's going to be this point C on the hodograph, which is certainly higher than the low-level flow. I indicate a low-level flow point on the hodograph over here, and then the C vector indicates where we have the storm motion low-level flow vector, and that really this line should align perfectly along the x-axis over here. That's the low-level flow vector. So if we want to compute the inflow vector, remember the inflow vector is just the flow vector subtracting out for storm motion, or the storm relative flow. That's the inflow. The inflow is how much flow the storm is feeling relative to its motion. So we have to subtract out the storm motion to get the inflow, or the storm relative flow, the low levels. Subtracting that out from the low-level flow, well, that's just going to give us a vector that goes, again, just like top minus bottom, from bottom to top, from our C vector, our storm motion vector, to our low-level flow vector, which is all going to be from the east to the west. In other words, storm is moving quickly from west to east, faster than the low-level flow, which is also coming out of the west. So storm is moving quickly from the west to the east relative to the low-level flow that's westerly, so it feels an easterly current of inflow in the low levels. No surprise there. We already talked about our horizontal vorticity. Our vortex tubes are going from south to north. Think of these horizontal vorticity, these vortex tubes, as slinkies. So all of our flow, all of our inflow to the storm is all cutting across the slinkies. It's not coming through the slinkies. It's not traveling along a helical trajectory to give it some spin in the ambient environment before it enters the convective updraft. It's just cutting right across these helical trajectories, or not attaining a helical trajectory as it's cutting across the vortex tubes completely. So with crosswise vorticity, the initial updraft is not rotating. Yes, sure, it tilted vorticity into the vertical to create vertical vorticity, but that initial updraft did not experience any inflow that was already helical. Its source inflow did not align with or reside along vortex tubes. There was no initial correlation between the updraft and the inflow and vorticity. Now later that may change, but initially the updraft and inflow, what was feeding that updraft, was all cutting across the slinkies, the vortex tubes, vortex lines, horizontal vorticity. So all that initial updraft is doing, it's not rotating, but it's redistributing horizontal vorticity into the vertical. Now let's consider, again, our westerly shear vector, resulting in our south to north horizontal vorticity that's being tilted into the vertical by our initial updraft that's not rotating, again, generating cross westerly shear flanking perturbation pressure deficits. One perturbation pressure deficit is to the right of the shear vector, one is to the left of the shear vector, with our cyclonic or upward vertical vorticity to the right of the shear vector, and our downward vertical vorticity to the left of the shear vector, or anticyclonic. Now, again, these are nonlinear shear perturbation pressures deficits, and they're generated from the now redistributed perturbation vertical vorticity aloft. Effectively, we've created two vacuum cleaners aloft, these perturbation pressure deficits, in the mid-levels that are flanking the initial non-rotating updraft. And they're along that vortex tube across the shear vector. So perturbation pressure deficits are flanking that initial updraft coming along the vortex tube that's been tilted into the vertical and lie across the shear vector, or to the south and to the north, or to the right and to the left of the shear vector. Now, these perturbation pressure deficits, remember the updraft from this incipient updraft is going to maximize in the middle to upper levels of the atmosphere. So these perturbation pressure deficits are going to maximize well above ground. Perturbation pressure deficits will maximize well above ground, mid to perhaps upper levels of the atmosphere. And think about that. We've suddenly created a mass deficit, perturbation pressure deficit, not only in the mid and upper levels of the atmosphere, but that's not happening where we lack an updraft right at the ground. So we get a vertical perturbation pressure gradient force that's directed upward towards the perturbation pressure deficits. So not only are we having air being drawn inward towards the axis of rotation, but also air is being drawn upward to fill these perturbation pressure deficits. And what that does is that generates new updrafts across the shear vector, flanking that initial updraft to the right and to the left. New updrafts form cross shear flanking that initial updraft along now the upward and downward vertical vorticity branches. So we have new updrafts that are forming along the vortex tube that's been carried into the vertical. And that, again, that negative perturbation pressure from nonlinear shear effects results in a hydrodynamic perturbation pressure gradient force that causes dynamic lifting. Again, that's that dynamic lifting that's occurring because of the perturbation pressure gradient force, comparing the perturbation pressure deficit in the mid-levels to that near the ground, which generates new updrafts that are now correlated or aligned with the vortex tube that's in the vertical. So there's kind of cause and effect going on here. We have the vertical vorticity that's causing new updrafts that are lying along the vorticity, the vortex tube. So you can kind of get some allusion here to the idea that we could be dealing with some nonlinearities. Things are happening with relationships to the causative factors that are going to reinforce their outcomes. We're going to talk about this in a little bit more. All this because the vortex tube is in the vertical. So these new updrafts, again, cross shear flanking updrafts, one to the south, one to the north, across the shear vector, these are now correlated or lie along the upward vorticity or the vertical vorticity that was tilted into the vertical. And what they're going to do is they're going to induce stretching of that vorticity. Think about it. The updrafts are going to be maximizing in the mid to upper levels of the atmosphere comparative to the impermeable boundary condition at the ground is going to result in stretching action for each of those updrafts along the vortex tubes, which is going to result in vorticity stretching and amplification of the vertical vorticity branches to the right and to the left of that incipient updraft. So these new updrafts stretch the vertical vorticity as they are now along the vortex tube branches in the vertical, causing, through that stretching process, the perturbation vertical vorticity to increase. What does that do? That's going to cause the perturbation pressure deficit from the nonlinear shear effect to strengthen. What happens is that the cross shear flanking updrafts strengthen. As those updrafts strengthen, stretching increases. The perturbation vertical vorticity increases. And we get a nonlinear feedback process that goes on and on and on to intensifying the updraft. So you might wonder, what eventually might get this process to stop? Well, in the real world, we know that our buoyant sectors are not infinite in expanse. Convection also eventually will be creating downdrafts and cold pools that create static stability in the environment that effectively short circuits this process. But in theory, this is a nonlinear process that results in updrafts, a rotating updraft intensification that continuously increases when how much CAPE did we need? Sufficient. That was it. We didn't need a tremendous amount of CAPE to get this ever increasing updraft, rotating updraft with vorticity stretching and further strengthening and perturbation pressure deficit magnitude strengthening as well that strengthens the updraft, etc. This process is effectively occurring in a manner that in the real atmosphere is manifest in low CAPE, high shear environments where we just need a sufficient amount of instability, buoyancy, that thermodynamic component of the perturbation pressure process to get going, such the dynamic part, the kinematic part, these hydrodynamic perturbation pressure gradient forces can get going from the updraft in shear effect. So the updraft interaction with the vertical shear of the horizontal wind through a deep layer, again in summary here, is going to result in new updrafts that flank the initial cell across the deep shear vector. So again, across the deep shear vector, again, talking about the shear here through a deep layer, the westerly shear that is going to result in that horizontal vorticity that gets tilted into the vertical, creating cross-shear flanking, new rotating updrafts, is going to be what we've addressed so far. No matter which way that vortex tube is oriented, that updraft mound causes the arch of the vortex tubes, and as we said, that nonlinear effect is going to be enhancing updrafts both to the right and to the left of that deep shear vector, regardless, just from the nonlinear shear term alone, of cyclonic versus anticyclonic, because the perturbation pressure is a deficit, as it's proportional to negative zeta prime squared. And so as a result, this explains the process of cell splitting. The cyclonic and right component, or right flanking cell relative to the deep shear, is going to rotate cyclonically and move off to the right, and the left one is going to do a similar behavior with an anticyclonic circulation. Again, this is going to be from the same magnitude negative perturbation pressure nonlinear shear effect occurring on both flanks with equal opposite rotating flanking cells. Again, nonlinear process here occurring because of the eventual co-alignment of the vorticity and the updraft, supporting the self-sustaining, self-reinforcing positive feedback, resulting in equal symmetric cell splitting for both the left and to the right of the shear vector. Again, what we talked about, what's really going on here is that updraft is bringing that shear-induced horizontal vorticity into the verticals. Effectively, that updraft is manifesting the horizontal vorticity from the vertical shear, creating a now outward-directed local centrifugal acceleration directed outward from the axis of rotation that needs to be balanced by an induced inward-directed perturbation pressure gradient force, an acceleration that will effectively result in the evacuation of mass by inducing a perturbation pressure deficit along the axis of rotation. This is going to be, again, the strongest where the rotation is strongest in the mid-levels, mid to upper levels, and it's the deeper shear profile through which the updraft intersects to support this process. So again, looking at this diagram, once again, the initial updraft, gray shading, is not rotating, but the subsequent cross-shear flanking updrafts that are aligned with the vertical vorticity, those are the ones that are rotating. Again, fundamental reason here is that for that initial updraft not to be rotating is that all of the vorticity is crosswise. The inflow is pointing from east to west, the horizontal vorticity is from south to north, and so all of the inflow that's converting into updraft material is lying across the vortex tubes and cannot become helical before entering the updraft, so all the vorticity is indeed crosswise. Now let's see what happens if we reorient our horizontal vorticity such that our inflow now lies along our vortex tube. So our slinkies, our vortex lines, vortex tubes, horizontal vorticity are all going to be lying parallel to our inflow for streamwise vorticity, and therefore our inflow can take a helical trajectory as it resides along our vortex tubes. In the case of streamwise vorticity, again, where our inflow is parallel to our horizontal vorticity. And in this case, where we have our inflow lying parallel to the horizontal vorticity, that incipient updraft can now be ingesting inflow that's helical in the environment and will immediately rotate. So streamwise vorticity is much more efficient at supporting updraft rotation than having to go through the whole process of that initial updraft that's not rotating, but it tilts vorticity into the vertical, and then we get new updrafts form, and then they rotate as they align with the now tilted vertical vorticity. With crosswise vorticity, that's less efficient. With streamwise vorticity, that's much more efficient. And the idea of understanding how the inflow vector is geometrically related to our horizontal vorticity vectors, that's all contained within the hodograph. Hodograph tells us about the horizontal vorticity, the inflow vector, the storm motion vector, the shear profile. Hodograph is such a vital consideration because these ideas of how efficiently updrafts rotate, how the storm splitting process evolves, whether we get a right or a left mover dominant, that's all in the hodograph. That's why this is so important to study and understand. Again, just a reminder, streamwise vorticity, in that case, the inflow is parallel to the vorticity. So let's consider a hodograph in this particular case that's no longer a straight hodograph, but one that has an arch or a concavity. I'm going to use this phrase concavity quite a bit. Remember, when we're talking about a concavity, we use a concavity to effectively describe an arch in some curve. And that arch, or rather, the way that arch is represented, on one side of that arch is the cave, that's the concave part, and the other side is the convex part relative to that arch. So this is a case where we have a concave southeast, convex northwest. So we're now going to insert a concavity in the lower part of this hodograph over here. And what we see is that we're going to take our storm motion vector, which is going to be our C vector, which is this dot over here, and we're going to compute the inflow vector, again, that's just going to go from the C vector to each of our hodograph points, our inflow in the lowest level or one of the lower levels, inflow at a higher level, still yet a higher level. And we see that with the horizontal vorticity being to the left of the hodograph, in almost every one of these, we have a notable component of our inflow that lies parallel to our dotted vortex tubes, or a horizontal vorticity, by providing that bow or that arch in the hodograph. And also providing that arch in the hodograph, if we placed the storm motion theoretically even on the hodograph, as we talked about in the crosswise vorticity case with a purely straight hodograph, because of that arch, we're still going to have at least some component of the inflow along our vortex tubes, indicating some component of the vorticity being streamwise because of the inherent arch. So that arch in the hodograph, the concavity, is very critical to understanding the concept of inflow's orientation relative to the horizontal vorticity and the tendency for streamwise vorticity to exist within the environment. So in this particular case, where we see the component of the inflow along our vorticity vectors, or vortex tubes, we see that there are levels where their helical inflow ingestion to the updraft will result in immediate updraft rotation. Well, there's some component that's crosswise, some component of the vorticity that's crosswise. There's also a component of the vorticity that is along the inflow for each of these points on the hodograph. And this concept of determining just how much of the inflow integrated throughout a layer of the atmosphere lies along the vorticity vector, which can be scaled by the vorticity vector in the layer in which we're computing this degree of streamwise vorticity, is simply a vertical integral of the dot product between the inflow and the horizontal vorticity, vertically integrated with height above ground. So remember, the dot product is looking at the component of the inflow along the horizontal vorticity scaled by the vorticity vector. And this, wherever the inflow is perpendicular to horizontal vorticity or crosswise, gives a 0 contribution. Wherever it is fully parallel, the inflow is parallel to the horizontal vorticity in the dot product, that gives us a much greater contribution for streamwise vorticity. So we're getting the idea that we take this dot product between the inflow vectors and the horizontal vorticity vectors and vertically integrate that from the bottom of the layer to the top of the layer. That's what we're going to try to measure in just a moment here. Well, that integrand that we just talked about is just a measure of the streamwise vorticity. How much inflow is actually along the horizontal vorticity vector times the magnitude of the vorticity vector. Well, doing some mathematics over here, what we see is when we take that dot product between that inflow vector, v minus c, and representation of the vorticity vector, what we can show is that that is just equal to the storm relative helicity and represents the dot product between the vorticity vector and the inflow vector. So in this particular case, we have a vorticity vector from west to east and an inflow vector from southwest to northeast with an angle theta between the two vectors. The component of the inflow along the slinkies, along the vorticity vectors, is computed by taking a dot product, as you can see here. So the storm relative helicity is just merely the sum of all of the components of the inflow along the vortex tubes multiplied by the magnitude of the vorticity. So effectively what I've shown here is by projecting that inflow vector onto the vorticity vector, we are able to compute the magnitude of the inflow vector times cosine of theta, which is going to be how much inflow is along our vorticity vector. When we multiply that or scale that by the magnitude of the vorticity vector, we're merely taking a dot product between the inflow vector and the vorticity vector, which we are computing by integrating the amount of inflow along each of these vorticity vectors. We integrate that to get the storm relative helicity. Wherever inflow is parallel to the horizontal vorticity, the integrand is non-zero and accumulates to non-zero storm relative helicity. So, in short, the storm relative helicity is just the total streamwise vorticity in a column of air bounded by the bottom of some layer, the top of some layer. It could be 0 to 1 kilometer for fixed layer. It could be the total amount of storm relative helicity or total amount of streamwise vorticity when the layer of air bounded by, at the bottom, the base of the effective inflow layer, and at the top, by the top of the effective inflow layer. And so this is a very important calculation, as this dot product allows us to really conceptualize what storm relative helicity is and relate it to the concept of stream. So let's think about this computation a little bit more. We're taking the vertical integral of inflow vectors dotted with horizontal vorticity vectors through a layer of the atmosphere. We're effectively summing up the component of inflow vectors along what the hodograph is determining to be our horizontal vorticity vectors. What this amounts to is that we're taking each of these inflow vectors and we're summing them up through a section of the hodograph, as that hodograph is always going to be determining, in addition to the shear profile, but the horizontal vorticity profile that's lying to the left of the hodograph, which means that we can show the storm relativity computed here is also proportional to the area under the hodograph swept out by the inflow vectors. Again, the inflow vectors, we're taking the dot product between those and the horizontal vorticity vectors that are all pointing to the left of the hodograph. As we take that vertical integral, we are determining not only storm relativity, but we're considering that as an area approximation under the hodograph. Again, we're just summing up inflow vectors within a layer of the hodograph. So for this particular case that we talked about here, where we have our storm motion that's lying on our unidirectional shear profile, in this particular case, all of our horizontal vorticity extends from south to north. If we were to compute the area under this hodograph, going from our point C to our lower level, and then C to our upper level within this layer, we wouldn't compute any area. No surprise, our inflow, which is all from east to west, varying in magnitude with the height above ground, lies perpendicular to our south to north horizontal vorticity. But when our initial updraft tilts that horizontal vorticity in the vertical, forcing new updrafts to form, we get deviant cell motion. One cell is moving, the new cell that forms to the right of that initial updraft relative to the shear vector is going to move in this direction, and then the one to the left of that shear vector is going to move in this direction over here. More to the left for the anticyclonic member, and more to the right for the cyclonic member over here. And now all of a sudden, we actually compute some area under the hodograph that's determined between that C vector, that storm motion vector resulting from the cell split, and the inflow vectors in the lower part of that hodograph, owing to the deviant motion of that right split off the hodograph at this point now, causing area to be swept out, and that corresponds also to some component of that inflow vector from C to the flow vector in the lower portion of the profile to have a parallel component to the south to north vorticity. And you can see that. That inflow vector over here is not just east-west, it's also more south to north, as well as our right split peels off to the right of our shear vector, and that is going to correspond to some component parallel to our meridional horizontal shear. Now again, for the case of some arch in the hodograph compared to the case of a purely straight hodograph, the case of the purely straight hodograph, we have to have that initial updraft that tilt the horizontal vorticity into the vertical in order to get new rotating updrafts, and then with those new rotating updrafts we concurrently have streamwise vorticity ingestion occurring, whereas this entire process is far more efficient from the beginning with an arched hodograph, because regardless of whether our initial storm motion is on the hodograph or not, we get area swept out by this hodograph. As you can see here in this triangle-looking area, if we were to connect a chord between these 2 points, we have area under this hodograph, which corresponds to the vertical integral of some non-zero dot product between the inflow vector and the horizontal vorticity vector. So this really illustrates the importance of understanding the hodograph, as the hodograph can tell us immediately how much inflow feed is going to be helical, going right into that updraft. That can go immediately into supporting rotating updraft. And as soon as we have that rotating updraft, all that positive feedback process from the nonlinear shear perturbation pressure component gets going. In other words, when we have that arched hodograph and we're using a representative storm motion that is going to be describing how the storm is moving, and we determine how much of area under that hodograph is associated with storm multiplicity, streamwise vorticity, ingestion, that is all going right into forcing that initial updraft to rotate that corresponds to the development of a perturbation pressure deficit from the shear effects and gets that entire nonlinear process going with the perturbation pressure deficit intensifying upon the stretching of the vertical vorticity that has been brought into, right off the bat, the ingestion of streamwise vorticity. Yes, there may be crosswise vorticity in an example. That would need to be tilted into the vertical to later correlate with updrafts for updraft rotation. But when we have that streamwise vorticity right off the bat from that arched hodograph example, then that nonlinear shear perturbation pressure term gets going immediately, and that really ties everything together. Yes, that nonlinear shear term can be operating for crosswise vorticity, but it gets immediately activated by the ingestion of streamwise vorticity, which, while there is that present for the splitting cells, that splitting cell case, that initial storm motion, it's not off the hodograph initially for the straight hodograph. It takes some time for the effects of crosswise vorticity, tilting, and new updraft formation to occur for that process to allow streamwise vorticity to be ingested to further activate the perturbation pressure term from nonlinear shear effects.